So what else can we do with an alpha carbon? We can do the aldol addition and aldol reaction, where with a base catalyzed, we can have the base come in and grab a alpha hydrogen, making the anion on the alpha carbon. We can draw a resonance structure, sending the electrons up to the oxygen. The enolate we just formed can go attack the carbonyl carbon of another molecule, and then in the end we can protonate that, and we've formed a beta hydroxyketone in this reaction. Okay, and in this aldol addition, it stops at the beta hydroxy carbonyl unless we have an aromatic ring in there where it would be conjugated to make the conjugated system. So ketones don't work very well in this, primarily where we have 80%, in this example, 80% of the starting material, 20% of the desired product in this. We can also go backwards from this, where we break the beta hydroxy compound apart back into the two parts, and then we can take off a hydrogen. We can reform the molecule of acetone and form an alpha anion, the enolate, and then that enolate can go grab a hydrogen off of water to form the other equivalent of our starting ketones. We can go back and forth depending on the conditions of the reaction. So the aldol addition, we form a beta hydroxyketone, as we said. The aldol condensation forms an alpha beta unsaturated ketone or aldehyde. Okay, in this case it's an aldehyde because we started with an aldehyde. So ketone or aldehyde, depending on what you start with. Okay, so as we showed before, we can draw it again, pull off the alpha hydrogen, make the anion, draw the resonance structure to make the enolate. The enolate can attack another equivalent to make the anion, and then this can go grab a hydrogen off of water to make the beta hydroxyketone. Now this beta hydroxyketone we can do a couple of different things with. If it were, we can do an E2 to eliminate to make that, or, and that's the easy mechanism because E2, there are no in between, no intermediates, or we can draw an E1CB where we can form the enolate and then send the electrons down from the oxygen to kick off the hydroxide on the beta carbon. Okay, so there's a couple ways we can draw that mechanism. Either way is fine if you were to draw it on a test. Okay, now for this to happen though, we really need an aromatic ring on there. So we can use an aldehyde or a ketone that has an alpha carbon with an alpha hydrogen on it, and we can use something that does not have an alpha hydrogen on it. So this way only one of the compounds can attack the other. We don't get a giant mix of possible compounds for products, but it's going to go through the beta hydroxy, but it's going to eliminate in the reaction all the way to the alpha beta unsaturated carbonyl, because we have that aromatic ring and it is fully conjugated between the aromatic ring, the carbon-carbon double bond, and the carbonyl. So it doesn't stop in the middle, it just keeps right on. So there, for this, we can do a crossed aldol, where, as I showed on the previous page, where we have one compound that has alpha hydrogens and one compound that doesn't have alpha hydrogens. And as long as only one of them has alpha hydrogens, we can control what happens in the reaction and only get one product. If both things had alpha hydrogens, it'd lead to a giant mess. Okay. So we can, with the propanol, we can add propanol to formaldehyde and add one carbon onto it with the OH to make the beta hydroxyaldehyde. If we use propanol and benzaldehyde, we can get the substituted cinnamaldehyde, okay, with the extra methyl on it. The second way we can do a crossed aldol is if we use a really strong base, like LDA, that has no ability to have an equilibrium going on. It's going to pull the hydrogen off and it's done. Then that enolate can go add to the other aldehyde to make the beta alkoxide, and then that can go grab a hydrogen off of water to finish off the reaction to make the beta hydroxyaldehyde or ketone. Okay? Primarily aldehydes, I should say. So we can control the reaction if we have mixed by what we do, what conditions we use, and what reagents we use for the reaction. We can do an intramolecular aldol where we're going to pull off one of the hydrogens. Now in this one, we have those two alpha hydrogens. It's symmetrical, so we have the same ones on the other side. But if we pull off let me draw it, change the color of the other one. Okay. If we think about the blue hydrogen, if we pull it off and it adds to the other carbonyl, we're going to form a 3-membered ring. If we pull off the red hydrogen and add it to the other carbonyl, we're going to form the 5-membered ring. So depending on what we want to do, we can control it and force it to go the way we want. We're not going to form a 3-membered ring in an aldol. It's much too small to happen. Okay, so, and we can draw all of those mechanisms. Let's draw. So now, what else can we do? We can do a Claisen condensation, and the only difference between the aldol and the Claisen is an aldol, you started with an aldehyde or ketone. With a Claisen, we start with an ester. So with an ester, we can have a strong base come in and grab the hydrogen to form, let's make the negative on the carbon. We can draw a resonance structure. The enolate can go add to another equivalent of ester to make something that looks like this with the tetrahedral intermediate, and then that can kick off ethoxide to make the beta keto ester. The beta keto ester has an acidic hydrogen there, so we can have ethoxide come pull that hydrogen off to make the enolate, and we need to get to there. And then in the second step of this, we add acid, and the acid protonates the central carbon, and we get our product of having the beta keto ester. And the mechanism is going to be the same every time we do this with an ester. So all we need to do is remove the alpha hydrogen, have the enolate attack something, and do you have to draw both resonance structures? No, you could draw the enolate and have the enolate go attack without showing the resonance structure of the alpha anion. Or you could do it the other way. Okay. I'd show both so you've seen it and you see what can happen. But we need to use whatever our ester is. In this case, it's the ethyl ester. So our base has to be ethoxide in ethanol so that we don't change the ester. Okay, if we use hydroxide, we run the risk of hydroxide adding to the carbonyl, forming the tetrahedral intermediate. Reforming the carbonyl, kicking out the leaving group of ethoxide. Ethoxide. And then the ethoxide or the hydroxide, either one, could come in to take the extra hydrogen off of the carboxylic acid to make the carboxylate. So if we don't use the exact same alcohol as what was in our ester, we run the risk of changing the starting material to something else, which is less helpful and makes a mess in that we'll get multiple products now. So we always want to be careful what base do we use with a Claisen condensation. One, let's start with benzaldehyde. Let's make cinnamaldehyde and add acetaldehyde and hydroxide. Okay, so the hydroxide, the only place we can start with is remove a hydrogen off of the acetaldehyde to make the enolate. The enolate can go add to the benzaldehyde carbon, sending the electrons up to the oxygen, giving us this beta alkoxide. It can grab a hydrogen off of the water we just formed to make the beta hydroxy. And then this beta hydroxy compound we could eliminate either an E1CB or an E2. We'll draw the E2 for this time. It's grab the hydrogen, form the double bond, kick off the leaving group. And there we have cinnamaldehyde. Okay. We could also draw it as an E1CB, and you should be able to draw either because you may see it either way as you're looking at notes. So if we didn't use the same one, here we have methoxide to show what can happen. We can make the tetrahedral intermediate with the OME and the OET, and then we can reform, kicking out the OET to get to the methyl ester. So unless we use the exact same alcohol as the ester, we run the risk of causing a lot of problems. Okay. Now the crossed Claisen is just like a mixed aldol in that we have to make sure only one of the esters has alpha hydrogens and one doesn't, so we don't get too many products in there. Or we use something like we used with the aldol, in that we have a strong base that makes the enolate without any equilibrium, so that there's nothing else that can happen. And that's what we show in these two. We also have the intramolecular Claisen condensation, the Diekmann condensation, where we will pull off an alpha hydrogen and cyclize that enolate on itself and then protonate it in the end. And what we make is, in this case, the enolate on the hydrogen drawn in. When it's removed, we'll add to the other carbonyl, and you'll make a 5-membered ring. In this case.